The following program is brought to you by Caltech.
Good evening, and welcome to tonight's Watson Lecture. My name is Ken Farley. I'm the chairman of the Division of Geological and Planetary Sciences here at Caltech, and it's my pleasure to introduce tonight's speaker, Jean-Philippe Avouac. Jean-Philippe is a professor of geology, and he has very wide-ranging interests in that field. His interests range from the study of the processes that occur when faults rupture to produce earthquakes, to the formation of topography of mountain ranges, which is also in many cases associated with earthquakes. And he was just telling me a moment ago about his recent interest in innovative methods of remote sensing of the Earth's surface and also recently of Mars. So a very diverse set of interests for geologists. Jean-Philippe is also the director of the Caltech Tectonics Observatory. And I want to say a couple of words about the Tectonics Observatory because it illustrates something special about the way Caltech works. So the observatory is a decade-long effort generously supported by the Gordon and Betty Moore Foundation, which has allowed about a dozen Caltech professors and about 20 students and postdocs to focus for an extended period of time, bringing their diversity of scientific interests and talents to processes occurring at plate boundaries. These are regions distributed all around the world, I'm sure Jean-Philippe will discuss them, where most of the geologic action on the Earth occurs. This is where most of the earthquakes occur, where most of the volcanoes occur, where mountains are built. It's clearly very important regions to understand, yet they are not especially well understood. And so the observatory has allowed this group to focus on them and also to deploy instruments, geophysical instruments that include seismometers and GPS receivers, for an extended period of time to produce a time series of the behavior of these regions. And that is a rich source of information that Jean-Philippe will talk about tonight. Oddly enough, the very first place where the observatory deployed instruments was in Sumatra, literally months before the biggest earthquake in many decades occurred in 2004. Sort of scary. We got these instruments in the ground, and a few months later, the biggest earthquake in decades. A real trove of unique information from that deployment and ensuing deployments over the last 5 or 6 years. So Jean-Philippe has done a fantastic job as director of that observatory. Before I give the floor over to him, I want to make a couple of announcements. The first is I was asked to announce an upcoming event called TEDx Caltech, which has the title Feynman's Vision, the Next 50 Years. This is an event that's taking place here in the Beckman Auditorium on January 14th, 2011. And if you're interested, you can check out the website tedxcaltech.com. I'll have to check that out because I don't know what it is here. What I do know something about is next month's Watson lecture, which is going to be more on earthquakes, but with a very different perspective, and that is a discussion of the consequences of earthquakes on the built environment, especially here in Los Angeles. Clearly an important topic. The speaker is Swami Krishnan, who's a professor of earthquake engineering, and the title of his talk is going to be Recreating the Great Fort Tejon Earthquake of 1857. And with that, I'll turn you over to Jean-Philippe, who's going to discuss rising mountains and sinking oceans, earthquakes that shape the Earth.
So thank you, Ken. So tonight, I'm going to talk about earthquakes and how they relate to the highest topography on Earth, the Himalaya, as well as to the lowest topography on Earth, oceanic trenches. Before I go to the core of the subject, I'd like to mention that at the end of the talk, you will have a chance to play with some of the toys that I will show in the talk. So you will see an earthquake machine, a sandbox to produce folding, and samples too, and you are welcome to have a look at those things in front of the auditorium. So now let's start with a personal note on how I became a geologist. Something like 25 years ago, I was an undergrad student in an engineering school in France, École Polytechnique, and at the time I thought I would become an economist or work in the industry. And I used to love hiking, and I went to Tibet for a hike during the summer, and I discovered this absolutely amazing landscape. And then I came back to school, and it just happened that a few months later, by chance, more or less, I walked through a hallway at the University of Paris, Jussieu, and I saw amazing pictures of Tibet on the wall. And then I discovered that people could make a living studying and traveling in those areas. And more or less, that's how I became a geologist. Sometime later, I signed up for graduate studies with Paul Tapenier, and I work with Gilles Pelzer too, who actually was sitting in the audience with a professor at UCLA today. And I was not sent to Tibet, but to the basement to do sandbox experiments. This kind of thing can happen. So since then, I've been always interested in trying to understand better how mountains form and how they relate to earthquake. And this topic, of course, has been a major topic since the very early days of modern geology. And one person who devoted quite some thought to the question is actually Charles Darwin. Charles Darwin, you may not know, was early in his career was actually a professional geologist. And when he was on the trip on the Beagle, he noticed evidence everywhere for uplift of land. And he saw these beautiful marine terraces in southern Chile, noticed that there were still very fresh shells on those benches, so indicating that the land must be rising very fast with respect to the sea level. Also, during that trip, he realized that oceans were sinking. He worked on the atoll in the Pacific. And so he figured out that there must be some connection between uplift of the land, sinking of the oceans, and also a connection with earthquake. He experienced during that trip the Conceptual earthquake of 1835, which is the equivalent, previous equivalent of the Maule earthquake, which occurred in Chile earlier this year in February. And so he had a try at connecting all these things. And he thought that there was some large-scale dynamics relating uplift of land, subsidence of ocean, and earthquakes. But because probably he was quite a smart person, he gave up on that subject and became a biologist. So there were too many pieces missing at the time to really understand this connection between mountain building, earthquakes, and how the oceans are evolving. The dominant theory about the evolution of the Earth and the formation of mountains was the theory that René Descartes proposed in the 17th century, according to which the Earth was evolving had evolved from initial molten state into a solid, and that this process would have led to the formation of a solidified outer shell, which would be contracting and crumpling due to thermal contraction. And that was the leading theory, and this theory has resisted time until the early 20th century. Today we know better. And one thing that is important that we've discovered only at the end of the 19th century is that there is heat produced inside the Earth. This is the effect of radioactivity. And because the Earth is this Earth engine, is this heat engine, you have convection happening within the mantle, and this can lead to a horizontal displacement at the Earth's surface. And we know today that continents have been dancing around at the surface of the planet over geological time. On this animation, time is indicated in million years. But the continents have moved around, bumped into each other, leading to collision, and that's a major reason for the formation of mountains on Earth. So a few words now about plate tectonics, which is now the current paradigm, now that we understand that you can have horizontal displacement at the Earth's surface. So what we have understood is that there are places at the middle of the oceans where mantle is rising up, melts, and produce new crust, basaltic crust, that will then move away from these mid-oceanic ridges. Okay? And as they move away, as the ocean floor moves away from the ridge, it cools down up to a point where it's dense enough that it can sink back into the mantle. And that's really what's driving plate tectonics. So now if you compare where earthquakes are happening and where you have topography with respect to the plate boundaries, you see an amazing correlation. Most of the earthquakes, the red dots actually, occur along those places where plates are either moving apart from each other or converging, for example, along the western edge of South America. The seafloor here is subducting beneath South America, and this is where you produce high topography, the Andes, on a lot of large earthquakes. Now there are things that we don't understand very well. And these are the questions that we're trying to address at the Tectonics Observatory at Caltech. We don't understand very well, for example, why is it that at some places you have very large earthquake, like the Sumatra earthquake of 2004, magnitude 9.2 earthquake, and whereas there are other places where the earthquakes are way smaller. Is it just by chance that we're not looking at a long enough catalog, or is it that there's a physical reason? These questions are not well understood today. Also, we realize when we look at this map of the seismicity of the world that there are places where there's quite a lot of earthquakes away from plate boundaries. That's the case in Central Asia, where you have a lot of high topography and a lot of earthquakes distributed. And we don't understand very well how this is working. So let's now go to the Himalaya. So fasten your belt, because the landing can be a little scary. So one thing in the Himalaya is that there is not much room for airport. And you may notice that the landing strip here is quite short. But, I mean, they have a clever system. It's sloping. Okay? So when the planes are landing, they are decelerated by the slope. And it avoids that they crash into the cliff that is behind me as I take the picture. So as soon as you get off the plane, you are in these beautiful valleys, and you see big boulders like those that are actually coming from the highest topography on the planet. These rocks are coming from the top of the Everest or in that area. And they're well-rounded, so they've traveled quite some distance. And sometimes among those rocks, you find some interesting rocks like these two, this black, well-rounded pebble, and actually I have one of those outside for you to look at later. And as a geologist, you take your favorite tool and you break the rock, of course. That's how you make discovery in geology. You break rocks to see what is inside. And what you see inside those rocks is very interesting. You see these ammonites. These are seashells. So that tells you something extremely important. That tells you that sometime in the back, some time ago, the highest topography on Earth today used to be under the sea. And actually, this observation has probably inspired one famous myth, Hindu myth, which is the story of Varaha, according to which Mother Earth, who is represented by this lady here, was once submerged by the sea and saved by Lord Vishnu, incarnated in this giant wild boar, who grabbed her from under the sea, grasped her with his tusk, and lifted her from under the sea. And the Himalaya would be the mark left by the tusk of Varaha. And what I love with this myth is that it really captures the geological history. So let's look at Varaha in action now. So what we know from plate tectonics is that something like 100 million years ago, India used to be close to Africa, Madagascar. And about 80 million years ago, it started to rift away from Africa and to drift northward at a very fast speed, which is represented here, of about 15 centimeters per year. And at the time, there was a sea between India and the rest of Eurasia. And that sea, the seafloor beneath that sea, was subducting beneath Eurasia. So you had volcanoes just like along the margin of the Andes today. And something like 50 million years ago, the two land masses came into contact, crashed against each other. And so what is important to understand here is that the seafloor is made of basalt that cool down and that can sink back into the mantle. But continents are made of lighter rocks that don't want to subduct. They stay at the surface. And so when two continents come into contact, you don't have one continent sinking back into the mantle. They're going to be squeezed against each other, and that's how you form high topography and high mountain range on the Earth today. So now, how is it working today? Because this process is going on. So this is a section across the Himalaya, more or less at the location of Kathmandu. And what this section is showing is that there's a lot of faults. All these lines are faults. Actually, there are many more than those that are represented on that sketch. Only the big ones are shown here. So all these rocks that are now forming the Himalaya have been deformed. And one question that we try to address is, how are these faults moving today? Are they all active, or are only a fraction of them active? How do they relate to earthquakes? One way to address that question consists in looking at the landscape. So here, you see a river, the Treasury River. And you may notice that on the side of the valley here, you have this horizontal bench. This is a river terrace. This is a former riverbed that was carved by the river. So what happens in the Himalaya is that the rivers are cutting down to compensate for uplift of land. And this is a view of another river, the Bagmati River. This is the modern river, and you can see bedrock here. And on top of that bedrock, you have gravel, river gravel, just the same as this one. So if you measure the difference in elevation between this gravel bed and the modern one, and estimate and measure the age at the time the river was flowing there, you know how fast the river is cutting down, and you can get an idea of how fast the land is moving up. And so we've done this kind of studies in the Himalaya that tells you how fast the folds at the front of the Himalaya are growing. So this is a cartoon explaining the principle of that study. So at some point you have a large valley that has formed this green terrace. Then, probably because climate is changing, the river tends to cut down into a narrower valley, and there will be remnants of the former valley left on the side. And these remnants are going to track deformation as a function of time, because they become passive marker of the deformation. So if you measure the geometry of that terrace that is now abandoned, dated, you can tell how fast this fold is growing. And actually you can tell how fast this package of rocks is sliding along that fold. So we've done that kind of studies in the Himalaya. This is one example of a fold. So here you have a measured fold that is routing at a depth of about 6 kilometers here. And here you have former riverbeds that have been folded by different amounts. The oldest riverbed here is about 9,000 years old, and it tells you that, and it's overhanging the present riverbed here by about 100 meters. So it tells you that the river is cutting down at more than 1 centimeter per year. So through some simple geometry, then you can infer how fast the rocks here are sliding up this fault. And when you do that, you get a rate of about 2 centimeters per year. Okay, so this fault is extremely active, 2 centimeters per year. This is about the same rate as on the San Andreas fault, a little less. So the interesting finding that we've made is that that's the only fault actually that is active in the Himalaya. You see a lot of other faults, but they don't affect the landscape as much. They are not as active. So it looks like all the action is taking place on that single fault, the red line here on that picture, and that all the Himalaya is thrust over that fault at a rate of about 2 centimeters per year. Now, how do we explain that we have all these faults in the back? And actually, you can do a simple experiment that will help you understand how this is working. If you put sand on the table and push the sand with a bulldozer, you're building a wedge. Okay? And so you can do that in the sandbox experiment, and you have the sandbox experiment outside. And what's going to happen is that the sand wedge is going to be pushed forward, and there will be sand layers here scraped off from the table and incorporated into the wedge. And this produces a beautiful set of folds, just like what you have in the Himalaya. And if you look at the detail here, only the frontal system is really active. Only the most frontal fold at any one time is really active. So this is what we see in the Himalaya. So you can reproduce the Himalaya in the sandbox at home if you wish. Now, is this a continuous, steady process? No. We have earthquakes, and earthquakes are due to the fact that deformation is not taking place smoothly. It takes place by sudden increments. For example, Kathmandu was destroyed in a major earthquake in 1934, and here you have pictures of Durbar Square in the Kathmandu Valley, taken before and after the earthquakes. A previous earthquake in 1255 actually killed the king of Nepal at the time. So there have been recurring large earthquakes in the Himalaya. So let's look at this map now, where we have put the rupture, we have indicated the rupture area of the large historical earthquakes in the Himalaya. So the first thing you see is that they actually align along the Himalaya. The other thing you see is that there are places where you don't have any large earthquakes. And so one question you may want to answer is whether those places could produce earthquakes in the future, or whether there are good reasons why they won't. Okay. But now let's focus a little bit on this most recent earthquake, the 2005 earthquake, which occurred in Kashmir, which is sort of a small earthquake compared to all the others we know of along the Himalaya, but which killed about 80,000 people. So this is a measurement of the deformation of the crust that this earthquake has produced. This was made by comparing images, optical images taken from satellite before and after the earthquake. And when you compare these images, you can see the fault trace, which runs over a distance of about 80 kilometers. And actually from these measurements, you can also tell by how much the fault has moved during the earthquake. So you can run a profile across these measurements, and what it tells you is that the land north to the northeast of the fault moved toward the south by about 5 meters at that point. Okay? So during this earthquake, there was an increment of thrusting along a fault, which is some equivalent of that fault I was describing earlier that is sliding at 2 centimeters per year. So the fault must be locked for a period of time and then slip suddenly during the earthquake. And to produce a 7.6 earthquake like this one, it takes only about 30 seconds. Okay. And so you have about 5 to 10 meters of slip on the fault. Now, why is it that sliding is stick slip? why is it that it's not smooth? And to demonstrate that, I've asked my two favorite assistants, Violette and Charlotte, to run an experiment for you, where you have a slider here, which is pulled by an elastic, so sort of a spring. And the slider is going to slide over the table. Okay? So let's play the movie and see what happens. So what you see is that the elastic is stretched, but it's not moving, and then suddenly it slides. And you can see that the resistance-proof structure here has collapsed during the process. Okay, that's when the accident happened, but anyway. So why is it that motion is stick-slip and is not continuous? It has to do with the friction law. It has to do with the fact that for most material, when you start sliding, friction is decreasing. And this is what this diagram is showing schematically. The idea is that when there is no sliding, the friction is relatively high. We call that the static friction. And as sliding occurs, it decreases. Generally, it's a function of the velocity at which sliding is occurring. It decreases to a lower value. And the result is that if the spring doesn't unload too fast, then you have an imbalance of force because the spring will have a force larger than the resistance due to friction at the base of the slider. So the result will be an acceleration of the slider. Okay? So that's how you produce earthquakes. So in a simple system like that, where you have only one slider pulled by one spring, what happens is that you have a periodic behavior. You have recurring equivalent earthquakes. And if earthquakes were like that, it would be easy to predict them. Okay? But earthquakes are not like that for the simple reason that the faults are not 1D. I mean, you can more or less imagine that a fault is more like a lot of these sliders that are linked together by springs. And so what happens is that an earthquake may start at one point, the slider might move, for example, and then it will load the neighboring sliders, and depending on the stress at the time this one moves, the neighbors will move or not. Okay? And as soon as you start to have more than one slider, the system becomes more complicated, it becomes chaotic, and you have all sorts of earthquakes with different magnitude occurring at different times. So rather than having a periodic behavior with recurring equivalent earthquake, you have a much more complicated pattern. Now, it's not necessary that friction decreases during sliding. There are conditions under which friction can increase during sliding. For example, it happens at high temperature. For most material at high temperature, they become more ductile, and in that case, friction tends to increase with sliding. It happens with granular medium, and in that case, also friction increases. And for certain minerals like talc, friction is actually velocity strengthening. The good thing with the velocity strengthening material is that when you do this experiment, you don't have earthquake at all. The fault is going to slide smoothly, and we would like faults to behave like that. So if you do that same experiment, what you would see is that the position of the slider would just increase slowly with time, no earthquake. So one thing that we would like to know is, on a particular fault, whether it behaves more like that, and we should not expect any earthquake, or whether it's stuck, and there is stress building up to be released in future earthquakes. And so the way to address that question is to use GPS. So in the Himalaya, we've deployed quite a lot of GPS stations, which look like that. So the antenna is there. It is anchored to the ground on this quadruped, which is drilled to a depth of a few meters. And these antennae are recording the position of that point as a function of time, and with a very high accuracy. And so when you look at the time series, you can see, so this is the position of some of the stations as a function of time, and you can see that the stations are moving north. You can see India drifting to the north as a function of time. And now, what I'm going to show is the velocity measured at some of these stations, which were deployed across that section near the Kathmandu Basin. And these are those points. So those points are showing the velocity measured at the GPS station, positive southward here and relative to India. So the 0 here is in India. So the points that are south of the Himalaya here do not move. They are sitting on the Indian plate. The points that are farther to the north in Tibet are moving south with respect to the Himalaya at a rate of about 2 centimeters per year, which is the rate of sliding on that major fault. And what you see is that in between, you have a gradual increase of velocity. So what it tells us is that we don't have an abrupt discontinuity. It tells us that actually the medium here is behaving elastically. It is that spring I was showing that is being compressed in that case at a rate of about 2 centimeters per year. So that fault is not creeping. It is accumulating stress to be released in future earthquakes. And when you do a modeling of this data, what you get is that the fault must root to some depth on a fault that is creeping continuously. This is the effect of temperature. The deeper you go in the earth, the higher is the temperature. You get to a point where the fault can creep smoothly at a rate of about 2 centimeters per year. And all this portion of the fault is locked. And this is where you need to have earthquake to transfer the slip on the strain that is building up here to slip at the surface. And this is what's happening during these very large Himalayan earthquakes. So in the interseismic period, what happens is that there is not much uplift. So here, what these points are showing is the uplift rate now, measured from geodesy. These points are not moving much, but you can see that these points are moving up here, right above the tip of that area that is creeping. So what happens is that in the interseismic period, as this fault is creeping at depth, there is strain build up, the Himalaya goes up a little bit, and then at the time of an earthquake, as it slides here, it goes down. And slip occurs along the fault. But as time accumulates slowly, the rocks here will move up the ramp and create the Himalaya. But it's a process during which you have uplift over hundreds of years, and then the sudden subsidence at the time of each earthquake. So this diagram is showing the difference between what's happening during the interseismic period as the system is being loaded by the 2 centimeters per year of convergence across the Himalaya. And this takes hundreds of years for stress to build up to a level where it can be released by major earthquake, magnitude 8 earthquake, and larger would then occur on the fault at depth. So now if we look in map view, we can detect from this GPS measurement where the fault is locked, and this is the yellow area. So the yellow area is all the place where the fault is stuck, is not sliding much. And this is where future earthquakes need to happen. An interesting feature here is that there's a lot of small earthquakes, which are shown by these circles here, and which happen along the edge of the lock zone. This is because there's a lot of stress building up at the tip of this creeping zone. So what happens is that you have earthquakes all the time in the Himalaya. Nearly every day you can measure a few tenths of decent earthquake. But once in a while, one of these small earthquakes become really big earthquakes, activating the world economy. So one thing we would like to understand better now is why is it that some earthquakes become really big? And why is it that some stay small and don't evolve? And the way to do that is to see in more detail how the fault is locked at places or might creep at some other places. At this point, we don't have enough geodetic measurement to really see the detail of the locking pattern of the fault. But this is something we've been able to do in Sumatra, and I'm going to address to show that in a minute. But before I move to Sumatra, one conclusion of what I've shown is that these gaps here, this one is particular, is accumulating stress to be released by future earthquakes. So for sure, this is not a creeping fault. There will be a major earthquake in the future in that area. So now let's move to Sumatra. So here we have the India and Australia plates subducting beneath Sumatra, and this is the oceanic trench here. So this is where the fault is reaching the surface at a rate of about 5 centimeters per year. And during that process, what happens is that the fault is locked, just like in the Himalaya, and so the land on top of it is subsiding. It's dragged down by the lower plate, which is subducting. And so it takes a few hundred years for stress to build up to the level where you have an earthquake on the plate interface. And at the time of the earthquake, the land rebounds, the islands go up, and it produces tsunami. This is exactly what happened during the 2004 earthquake and the subsequent large earthquake which have happened there. So we are monitoring this process in Sumatra using GPS, and this is what we measure with our GPS stations. This is position as a function of time. This is the interseismic period during which stress is building up. And so the points here move away from the sea as a function of time, and at the time of earthquake, they move suddenly back toward the sea. And this is what producing the earthquake and the tsunami. We are monitoring that with GPS, but also by looking at coral reefs that are fringing those islands, and you can use the coral to tell how fast the land is subsiding or uplifting. And so what is interesting in Sumatra is that we can see the detail of how the fault is locked at depth. And this is what is shown on this cartoon. The red areas are the areas where the fault is fully locked. There is absolutely no sliding between the two plates. The white areas are the areas where actually the fault is sliding at the long-term slip rate. And the result is that those places should not accumulate stress to be released in future earthquake. The places where stress is building up are the red areas. And so you can compare this pattern of locking of the plate interface with the area the areas that rupture during earthquakes. And we can make that comparison in that area that produced magnitude 8.7 earthquake in 2007, the Nias earthquake. So what happened during that earthquake is that the island, which was subsiding, as I shown on the animation before the earthquake, you can see that the trees were dying because they were slowly being submerged by the sea. This island went up quite a lot at the time of the earthquake, and you can see that all this area that used to be the laguna is now dry land. So during that earthquake, this is the area that actually slipped. Okay, the color is indicating the amount of slip on the fault, and it slipped by as much as 12 meters locally. So this is something similar to, although bigger, to the Kashmir earthquake. What is interesting is that with our GPS, we could detect also the slow displacements which occurred after the earthquakes. Okay? The GPS stations are showing that not only you had a sudden motion at the time of the earthquake toward the sea, but also it continues, the stations continued to move toward the sea after the earthquake. And actually that's telling us that the area surrounding the rupture actually started to creep slowly after the earthquake, and this is what the color are showing here. So all the shallow part here near the trench didn't slip during the earthquake. It started to slide after the earthquake, but slowly, without producing any seismic waves. And so what is interesting here is that first we see a pattern. We see that there are places where the behavior is velocity weakening. So like in the experiment I was showing with the earthquake machine earlier, these are these areas, and this is where the earthquake happened, and you have areas that are velocity strengthening that creep without producing earthquakes, in particular near the trench here. So you have this pattern. And one good thing here is that if you detect this pattern using all the techniques I've described, then you can be a little predictive. You can see that the Nias earthquake ruptured the area that was locked before the earthquake. So with this approach, you cannot tell when an earthquake might happen, but you might say something about where it could happen, and you can say something about how much energy is available to be released in a coming earthquake, which is already quite valuable information. So after we made that studies, we pointed to that area, which is also quite red spot, where we knew major earthquakes had happened in the past, in 1833 and another one in 1797, magnitude 8.5 earthquake minimum. And the expectation was that the area was ready to produce another earthquakes like those historical earthquakes. The surprise was that it did produce a large earthquake in 2007, but the earthquake was way smaller than the previous earthquake in the area. It ruptured only a small fraction of that red spot. Okay, so the first thing you can say is that, wow, here it looks simple. You see a lock patches, it ruptures, it's predictable in a way. Here it's very different. Here you have a much more complicated pattern. And once you may have a big earthquake rupturing the whole thing, and then later on this area could rupture in many smaller earthquakes. And this is what's happening. The 2007 earthquake ruptured that area. It triggered another earthquake of magnitude 7.9 here, and you may have heard about this earthquake earlier this week, which occurred right here, which also produced quite a big tsunami. The thing is that there's still this area that remains to rupture, and there could be a magnitude 8.5 any time in that area. And here you have something like 1 million people living along the seashore, ready to be swiped out by a tsunami. Now, what is the emerging picture from the studies I've described? The emerging picture is that faults are probably made of a patchwork of areas that can be seismic, the pink areas, where friction is decreasing during sliding, so where earthquake can nucleate and propagate, and the areas that are rate velocity strengthening, white, where the plate interface tend to slide smoothly without producing earthquake. And the good thing is that we can start to image that pattern using, in particular, geodesy. We can see sort of guess what is the geometry of those things. Now the question is, what can we do once we see that? And also something I didn't mention is that we can also measure the friction properties. We can measure deformation, we can estimate stress, so we can have a quantitative estimate of what the friction level is and how it varies with sliding. So we can make physics here. And now the question is how to use that to say something useful for earthquake hazard. As we have seen with the example in Sumatra, it's not a simple thing. You cannot just say we have a pink patch here and it's going to rupture exactly in that area and we're going to tell you when and what size will be the earthquake. No, it's more complicated than that. And the problem is that all these patches, they interact. It's a little bit like these sliders I was showing earlier. They may sometimes rupture together and sometimes they may not. And actually this is a question that can be addressed from doing numerical experiment, dynamic modeling, using techniques that have been developed in particular at Caltech by my colleague Nadia Lapusta, and Pablo Amparo is developing these kind of things too. And here is an example of an experiment where it looks very simple. We have a big fault, okay, which is representing the megathrust in Sumatra or in the Himalaya. And then we imagine that the gray area is the equivalent of the white area in my previous slide. It allows the fault to slide without producing earthquake. And then we have the pink areas. The pink areas are where sliding is decreasing, where friction is decreasing during sliding. And so this is where earthquake can happen. And so that's where they nucleate and they propagate. And so let's look at the result of this kind of experiment. So time is not linear. So here we have stress building up for something like 50 years. And then you have an earthquake nucleating here. So suddenly the speed of the movie slows down. So you have a frame every second or so. And what you see is that the first earthquake ruptured the whole thing. The two patches went together, despite the fact that in between you have a smaller area that is rate strengthening. Then you have a different earthquake nucleating here, And you see it's very different from the previous one because the stress left from the previous earthquake has changed the conditions for propagation of the next earthquake. And you see that this one stops at the barrier here and trigger another earthquake on the other side. And so here with this numerical experiment, you can see a quite complicated pattern. So the future in that field might be that from the observation that we can make using geodesy, field geology, and so on, we can sort of estimate the physical properties, what friction to put in this experiment, in this numerical experiment, what geometry to put, where are the places that are rate weakening that can produce earthquake, nucleate earthquake. But what we won't probably be able to do any soon is predict the next earthquake. But what we can do is run scenarios like this one and see what kind of behavior we have on the long term. And we do have patterns here. We do have patterns that can be extremely useful to evaluate what kind of earthquake could happen at a particular location. So down the road, we can imagine that we will do like in meteorology, we would incorporate, assimilate our geodetic measurements, seismological measurements into this kind of modeling to be able to say something about how faults are going to evolve in the future. So I think it's about time to conclude, and I would like to thank all the people who have contributed to the research I've shown today. A number of students and postdocs have done very hard work on these things. My colleagues, faculty in the GPS division, and all the people who make the Tectonics Observatory a success. And last but not last, Tim Pyle, who's helped prepare all these nice animations that I've been showing today, and Catherine Stebbins will help with the graphics. So thank you very much for your attention, and make sure you enjoy the display that is at front of the auditorium. Thank you very much.